So, yeah, I started working here, in the fall. The year before that, I was working in a government, research lab for the Navy for a year. Before that, I taught math at Liberty University from like 2008 to 2019. So what's the majority of what's on my YouTube channel is from my teaching there, and so.
Where'd you go to school and stuff?
Well, when I was a teenager, my dad said that I could either pay rent or go to school, and I said fine. So I went and I took classes at the local community college. I tried to do electrical because I had no English requirement, but then I guess I had good placement scores or something, so they put me into electronics, which had 2 Englishes, which I wasn't super happy about, but I kind of dealt with it, see the problem. And anyway, that was super fun because that's where I discovered physics, and so like David Pittman was my teacher, and he was just a great teacher and just made physics interesting, and it kind of hit me that you could only understand physics with math. And just the interplay between physics and math really stood out to me, and I kind of became addicted. And then I thought I wanted to be an electrical engineer for a time, so I went to NC State as an undergraduate. So I spent 3 years at NC State as an undergraduate, started in electrical engineering, and I changed my major to physics after that because I was interested, and then all of a sudden I realized, wait a minute, I should also be a math major, so I double majored in math and physics. I wanted to know what string theory was because, well, my first goal was to understand general relativity. And so yeah, but I by the time I was done undergraduate, we had harassed the math department into letting us take general relativity. We got a bunch of people together and just kept like saying, hey, we want a course, because they hadn't run it for a couple of years, but thankfully they did run it, and the guy who taught it was great, just great. Dr. Oh yeah? So are you a physics major? Or?
Physics major.
Oh,
We're fighting just for an extra class.
Yes, I should know we don't have a physics major. But so neither does Liberty. But anyway, so yeah, actually I was promised to be able to teach modern physics about 10 years ago. It never happened. I wasn't happy about that because that would have been fun to teach. But anyway. Yeah. So where was I? So I felt like I was happy. I felt like I had some decent understanding of general relativity as an undergraduate because I'd taken enough math. For example, the math we're doing right now is exactly the math you need to start to understand general relativity, because the mathematics of general relativity is calculus on curved spaces. And that's not exactly what we're doing in here, but what we're doing is a precursor to that. To best understand manifold theory, you should first study some elementary differential geometry, and that's what this course is mostly. But we will touch on manifold theory in here. It's not far from what we're going to be doing. In fact, we'll even define a manifold later and give some elementary examples. But nowadays, there are beautiful books on manifold theory that are really good for self-study, like John Lee's book is fantastic. That sort of thing wasn't around when I was an undergraduate, so we were kind of more dependent on professors. But I had some really fantastic professors, undergraduate and graduate. Anyway, so having understood what I wanted to about general relativity, I then became interested in what came after that. And so it was string theory. I read some books like Mikhail Kaku's, I'm sure I'm mispronouncing his name. He had a book called Hyperspace, where, talks about hidden dimensions and all that kind of mathematics. Like, basically, it's a string shot of string theory, circa 1990, something like that. Anyway, so that book and others really captured my imagination. I wanted to know more about the string theory, so I went to Stony Brook because that's one of the few places that you can go and take classes on string theory. Unless you're like, just a phenomenal student. I mean, you can, I just applied to any place I thought I could study string theory, like take classes on it, So like I applied to Princeton, Harvard, Yale, They all have wonderful rejection letters. Like I think they're actually signed, they're on nice paper. It may have cost me $50 to $75 for the application fee, but the rejection letter was like beautiful. And they offered me to come back and work for them later. So, they're very magnanimous. But no, Stony Brook was good. It was good for a couple of years. But somewhere in there, I realized that I wanted to do math. And so I went back to NC State and studied sort of mathematical physics with Dr. Fulp, who was one of my, or probably my favorite professor as an undergraduate. My doctorate's in something called super math. It's basically, how to say it quickly? It's mathematics which supports the calculus that you do in string theory. It's not the dominant viewpoint the way I did it. Like the dominant viewpoint is something called algebraic geometry. And in fact, what is string theory now? I have no idea. Like string theory reinvents itself every 2 years. String theory is like the blob. It just keeps like sucking in new, new theoretical things. It is a moving target. So anyway, to get to the forefront of theoretical physics nowadays, you pretty much have to have a PhD in math in order to understand it at this point. It was that way 15 years ago. It's only gotten worse. But yeah, that's a snapshot. But I love teaching math. When I was a student, I only cared about calculations. Like, for example, I took real analysis. Real analysis where I was, it was entitled Advanced Calculus. So I love calculus. I learned, product rule, quotient rule, chain rule, integration, all this, all these problems you can solve, work done by variable force, all these interesting things, right? So I was excited. I was going to go take advanced calculus and learn advanced calculus. It was not advanced calculus. It was proving things that were obvious with great effort. And whenever I talk about this, I always bring this up because I'm still bitter about it. I turn in a homework. I say, let C be a real number, blah, 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 blah. I say A less than C, C less than B, therefore A less than B by transitive property. Points taken off. Like what? What's that? Well, you didn't say C was a real number. I said C was a real number up there. We read proofs top down. What do you mean I didn't say C was a real number? Well, you should emphasize it at this point. Just, see, I'm still angry about it. So I try not to be that. So I try to make the focus of my math courses about the part that's interesting in as much as I can. But nevertheless, we do have to give definitions and prove some things, right? So otherwise, at some point, it gets super fuzzy, right? So that's a little bit about me. I'm married. I have 5 wonderful children. And yeah, their pictures are all on the website that is not showing correctly at the moment. But and I've recently, in recent news, I've recently purchased this A71 5G, which I'm pretty excited about. Well, I'm not that excited about it. My kids are excited about it because they can play Fortnite on it. So like Matthew's always like, "Can I have your phone, Daddy?" Like, yes, Matthew. And then I lose my phone to the Fortnite, Well, it's pretty neat. What these things can do these days. All right, now I'm behind, but it was for a good cause. But I look forward to getting to know you guys faster as we go on here. So I'm going to start by talking about synthetic. If I spelled that right, I don't know. Versus analytic geometry. That's roughly the theme of what I'm about to tell you. But first, I just want to take a trip down memory lane, all right? And I want to talk about a Euclidean geometry. What is Euclidean geometry? So Euclidean geometry is encapsulated, of course, first in the books of Euclid, right? Euclid's Elements. And, this was written down, what, a couple hundred years before Christ, I think. I don't know, like, was it? I don't know, I can't remember the exact date. I feel like it was 300 or 400 BC. But in any event, in Euclid's Elements, he gives this list of terms, of basic things, right? And so I'm just going to rattle them off. I'm not going to write them down. He says, a point is that which has no part. A line is a breadthless length. The extremities of a line are points. All right? A straight line is a line which lies evenly with points on itself. So when I read this in the first book I read this in, I was like, what? What does that mean, So I'm grateful. So what I'm reading you right now is from A Gateway to Modern Geometry, which is by Saul Stahl. And this is a person who absolutely deeply loves analytic, synthetic geometry, really, and also analytic geometry. This is the master work on this stuff, I think. But this book is really mostly about what's something called the Poincare half-plane, which I'll be talking a little bit about. But let me stop saying that. Anyway, what I'm just telling you is that this list I'm giving you right now is from that book, and I'll try to make a scan of the pages that are most relevant to what I'm saying and give it to you just so you have it for reference. It's fair use, I think. So I said before that a line is a breadthless length, right? So when Euclid says line in this item here, he doesn't actually mean a straight line. He's actually talking about a curve. So like even in Euclid, there's this idea of a curve, because later he has a straight line is a line which lies evenly with points on itself, right? So like a straight line, in a curve, it doesn't lie evenly on itself, right? So what does exactly that mean? You see, even in Euclid, which is sort of the, best example of careful mathematics of that time, there are very nebulous phrases, really, when you get right down to it, right? The extremities of a surface are lines. Before he said that the extremities of a line are points, right? So there's this concept of extremity. I think nowadays we tend to say boundary, right? Does a surface necessarily have a boundary? How about the xy plane? That's a surface. What's its boundary? Yeah, it's at infinity. I mean, there is no boundary, really. Apparently, in Euclid's discussion, surface, he has in mind here a finite surface, right? But lines, he also has this, I'll see if I can get to it. A line, when lines, excuse me, I've lost it. Oh, I'm sorry, I'm getting ahead of myself. I'm getting ahead of myself to the postulates. I'm still talking about the basic terms for the moment. A plane angle is the inclination to one another of two lines in a plane which meet another and do not lie in a straight line. I read these sentences, I'm like, what? I mean, I know an angle when I see one, right? But I don't see it in the sentence I just read. Now this makes sense. Well, one more thing. When lines containing an angle are straight, then the angle is called rectilineal. So see, even in Euclid, he has the idea of curves coming together and talking about the angle between curves. But Stahl mentions that he introduces this concept, but it's almost nowhere talked about in his Elements. So it points to a larger discussion in Greek mathematics that they were looking at curves that were probably not lines, and talking about how do the angles between lines that meet, the curves that meet at angles actually work, right? But apparently they didn't find anything interesting enough for Euclid to record more about it, right? We should remember Euclid's kind of like an encyclopedia of his time. It's not all his work, right? He's recording down what was known at that time. This one's interesting. When adjacent equal angles to straight lines meet, if you have two adjacent angles to a straight line, what are those called? Those are called? If we have a straight line and we have another line go through it, but this angle and this angle are matching, what is this? My picture's wrong, right? Yeah, that's a right angle, right? And then he defines obtuse angle, acute angle, boundary figure, a circle is a plane figure, all these things. Eventually, though, when Euclid gets done introducing all the basic objects, right, from lines to points to surfaces and so forth, at some point he starts listing things that must be true. They're just obviously true about geometry as he envisioned it, as they envisioned it. And here's what those were. Those are called postulates, right? These are things that are basic, that can't be these are fundamental truths of Euclidean geometry, right? These are basic. Number one. You could also say a postulate is an unexplained theorem, you know? To draw a straight line from any point to any point. By the way, I'm going to start abbreviating straight line SL because we're going to say it enough that I'm going to get really tired of writing straight line. To draw a straight line from any point to any point. Two, to produce a finite straight line containing continuously in a straight line. So postulate one is kind of clear, right? I mean, it's saying you give me 2 points in the plane where we're going to, talk about this plane geometry. There's a line that connects those 2 points, right? That's postulate one. What's postulate two say? To produce a finite straight line continuously in a straight line. So apparently, what this is getting at is the idea that if you have a line segment, you can keep making it longer and longer and longer and longer in a continuous fashion. Like you can just keep extending it continuously. Now that word continuous in this context is very kind of vague, right? I mean, it's... Have you guys had real analysis? Are you currently taking it or you've already taken it? Took it last semester. So as you know, the definition of continuity is not fuzzy, is it? It's pretty unbending and unflinching, isn't it? Right? Yeah. This is not that kind of use of that word, is it? Right? This is the fuzzy precursor of that. Axiom 3. To describe a circle with any center and distance. All right. And so sometimes I think this is, I think when I take in high school geometry, basically this came down to you're allowed to use a compass, But I think there's a danger in that, in the sense that the idea here is not that you can take the compass. Like if you actually had I wish I had one of those. I should have found a compass. You see one of those giant classroom compasses in here anywhere? Sometimes it's a physics classroom. They sometimes need a compass for their drawing, You see one back there anywhere, lying around? I don't see any. But I guess I could break this in half and make one. Probably shouldn't do that. Anyway, the point is, if you have a compass, which, now this is really bothering me. See, ordinarily I've gotten so used to working with markers, I usually have a bag of markers with me so I can make them. How many markers? Do they stick together? Like, can you? Will they stick one to the other though? Can you build a? Aha! If you can give me 4 of those, then I'll be in business. I'll return them when I'm done. But what I'm getting at here is the compass is such that you can't pick it up and keep it in place, right? Because, perfect. Thank you. If you think about it, right? If we had a compass like this, right? And we could fix this circle and draw the circle around that point, whatever. Wait a minute. Oh, that's symmetric. So let's see here if I can do it. Kind of draw that circle around. So if I could, fix the center point and draw the circle, right? If I could hold that compass in place like so, right? And I could just move it over here like this, then I'd have another point right here, which was exactly the same distance as the center point, right? Like this distance and this distance, they'd be equal if you could keep the compass from sliding. But that's not how the compass in this postulate works, right? It's so he says you should think of it as like a collapsible compass, which actually that's kind of a good example of a collapsible compass, right? Because I can't keep it steady. I can't even draw. I couldn't even draw a circle. But so anyway, so to describe a circle with any center and distance. Now, what this sentence means is that if you give me a point and you give me a radius of the circle, then you can construct the circle that has that distance and that center point around. Like that's what this postulate's meaning. Postulate 4, what's postulate 4? That all right angles are equal to one another. Now, see this word equal, it begs a larger discussion, which I'm not going to have with you here. There's actually a lot of debate about what exactly Euclid meant by different things. And if you want to start getting into that, I recommend this book by Saul Stahl is fantastic. It's very easy to read if you're interested in this stuff. This is not what the course really is. This is just this is a warm-up, all right? An appetizer, I guess you could say. Let's see here. So then that brings us, so these are the 4 initial postulates, right? And then there's the 5th postulate. Postulate 5, which I'll write up here, is the following: that, and this is how it was stated in Euclid's Elements, all right? That if a straight line falling on 2 straight lines make the interior angles on the same side less than two right angles in sum, then, goodness gracious, this thing is endless. The two straight lines if produced indefinitely meet on that side. Meet on that side, which the angle's less than the two right angles. Ay, ay, ay. On which the angle's less. All right, so have you ever heard this parallel postulate before? I mean, this is called the parallel postulate. Have you ever seen it stated like this? I mean, here's a picture of it. So you got these two lines that meet over there, right? If you draw this line, right? So this angle and this angle, if you take the sum of those, it's what? It's less than the sum of two right angles, right? Then on that side, these two lines have to intersect. So this is postulate 5. Now, I mean, look at these postulates. I mean, there's the various vagaries here, right? But in contrast, like postulate 5 is like, what? And so people have had that feeling for a long, long time. And mathematicians for centuries tried to prove that this postulate was not necessary because it's what? It's kind of ugly, right? So if you could prove that this was just a consequence of these guys, logically, right, then great. You don't need that postulate anymore, right? So there are other ways to restate this postulate. And so this one's kind of a pain, and for this larger discussion, we don't like this one. It's better to replace this for the sake of our larger discussion with the equivalent postulate, which is known as Playfair's postulate. Playfair's postulate. And Stahl tells us that it actually wasn't due to Playfair. It's actually due to Proclus of the 5th century, actually. And here it is. This is the one that I think I've seen before studying for your class. Given straight line M and point P, I'll give it a big P with a little foot on it there, not on M. There exists a unique line N that contains P and is parallel to M. Now that, you can see why that's called the parallel postulate, right? What does it say? It says, let me draw the picture of it. That one, the picture is easier to understand. So you have a straight line M. I'll start with that, right? You take a point P, like not on M, right? Like here. And what does the Playfair's postulate says? It says that there exists a unique line N which goes through P, right? And what does it mean? What does it mean for that line to be parallel? What does that word parallel mean in this? I mean, like, well, you never really defined parallel, did you? What is a parallel line? Never intersecting, right? Now, there's at least probably a dozen well-known equivalent statements for the parallel postulate, so like I said, there's flaws in Euclid's original treatment. The person who kind of redid it carefully and sort of settled the mathematics of this was Hilbert. In 1899, he wrote Foundations of Geometry, which is sort of recognized as the sort of last will and testament of this discussion in terms of like the axiomatization, the careful axiomatization of these things. But no one teaches that because it's like pedagogically horrible. It's very technical. And but anyway, just to mention that. So Hilbert fixed Euclid, and you can look at page 17 of Stahl's book for Hilbert's axiomatization. All right, so great. Now, one of the interesting things that happened in the history here was as people tried to prove this was true, right? What they did to try to prove that this was true, they assumed something related to it was equivalent was wrong. And so they assumed something that was, like a twist of this, they assumed like it was true, hoping that in assuming something that was not this was true, they would find a contradiction, right? And there's a mathematician, I want to say Italian, Saccari, and he proved this like bunch of theorems in the hope of finding a contradiction, right? And if he found a contradiction, and he eventually did find a contradiction, but actually that contradiction was flawed, so he tricked himself into thinking he had a proof that the parallel postulate followed logically from the first four. Actually, it does not. I will show you proof positive that it does not. All right. But he actually, in his attempt to prove that the fifth postulate comes from the first four, he actually found all these theorems, which in retrospect are theorems that are true for non-Euclidean geometries. So it's kind of it's a very funny thing to look back on it. So sometimes people will say things like Saccari invented hyperbolic geometry because he found these theorems. I think that's maybe a little bit too optimistic in some sense view of what he was doing. But anyway, I'll just get to the point here. There are other models, all right, there are other sets, if you will, where we can define a line, a circle, a point, all right, and distance, all right, an angle. We can do those things. We can get alternative definitions for line, circle, distance, point. And with respect to those alternative definitions and this different model, we still get adherence to postulates 1, 2, 3, and 4. Like all of these things are still satisfied by the model I'm about to show you. However, in this model, that does not happen. Playfair's postulate's not the case. So, just to be brief, there's something called the hyperbolic plane. And so to describe the hyperbolic plane, I'm going to use analytic geometry. So you notice, by the way, all of this stuff I've been talking about, have I written even one equation? Not really, right? I mean, we talked about, there is something there, like he does have some concept of measure, like angles being equal. There's some kind of numerical underpinning, but it's never quite explicit in Euclid. And that's the problem. Since the time of Descartes, we've been using numbers to link up the points, right? This is the fundamental thing with analytic geometry, is the idea that we can, take a pair of numbers or whatever and uniquely correspond to a point, right? And then we can describe geometric things with equations. This is analytic geometry. But we can also use the ideas of analytic geometry to make non-standard definitions, and that's what the hyperbolic plane is. It's like the hyperbolic plane is literally as a point set. It's just, I'm going to use h for it. It's equal to, let's say, x and y in R2, all right, such that y is greater than 0. So listen, guys, what I'm going to do for about the next 10 minutes is I'm just going to rattle off results about this hyperbolic plane. I'm not going to prove anything, all right? But I want you to appreciate just what this thing has, all right? So that's it as a point set. It's just the upper half plane with the x-axis deleted, all right? And so it's just this space is h. And, okay, great. What's the distance? So here's the distance formula. The distance in the hyperbolic sense of a curve gamma is equal to the integral of gamma of the square root of dx squared plus dy squared over y. Now, the way Stahl explains this is to think of it getting infinitely cold. Think of it getting infinitely cold as you get to the x-axis, and everything slows down and down and down, and everything becomes longer and longer and longer as you get closer to the x-axis. You never actually get to the x-axis, but.
Can you describe the plane again? You said remove the y-axis?
Remove the x-axis. It's the upper half plane. In terms of Cartesian products, H is the reals, Cartesian product with 0 to infinity. So it's like all x's, but y's are only positive. So, all right. Now, I said that you can define straight line, you can define circle, you can define right angles in the hyperbolic plane, all right? So this is just the distance of a curve. And it's just calculus. You can work it out. Let's see here. I think I can I can safely erase the much more cumbersome fifth of Euclid. And so, like, here's proposition 4.11 in Stahl. I'll draw a picture. If we have a circle, and every time I say circle here, I actually do mean circle as you're used to it in the plane, okay? But if you have a circle like this, and it centers on the x-axis, all right? It centers on the x-axis, so let's see c comma 0. And then you have 2 points out here, like a point Q and a point over here, P. All right? And then you measure the angle from the positive x-axis in the usual way. So standard angle alpha and standard angle beta. So alpha less than beta. All right? And you calculate the length of this arc, this guy right here. You work out that integral. And what it gives you, let me call this thing gamma. I'll call it gamma QP. So the distance in the hyperbolic sense of the curve, this arc, QP, it turns out equal to the natural log of cosecant beta minus cotangent beta divided by cosecant alpha minus cotangent alpha. You're like, well, obviously. right? No. So in Euclidean geometry, if you have a circular sector, right, between two angles, like if you drew the same picture and you, say, expanded out to a bigger circle, right? Like what if we went out to like this circle out here, right? And you looked at, say, from here, Q prime, over here to P prime. In the Euclidean sense, the length of this arc out here, right, would definitely be longer than the length of the closer arc, right? Because the radius is bigger. If you have a bigger radius and the same change in angle, we know the formula, S equals R times change in theta, right? R theta is the arc length subtended in a circular arc. This is Euclidean geometry. So in the Euclidean sense, that arc out there from Q prime to P prime is longer, right? But what about in the hyperbolic sense? See this formula? Does it care which one's P and which one's P prime? It doesn't. It's just based on the angle. This is a really weird formula. This says that the length of the arc is just based on the angle change. That's weird. That's really, really weird. It's also not part of Euclidean geometry, so yes, it's divorced from our intuition a bit. Another result is if you were to look at, I'll put it over here, if you look at, say, going from here to here, so let's say that point is A, Y1 to A, Y2. All right, let me call this line segment, vertical line segment, I'll call it L. The distance in the hyperbolic sense of L, it's just equal to the natural log of Y2 over Y1. So I'm probably going to make this one of your homeworks because I think that calculation won't be too onerous and it'll help make part of what I'm saying more concrete to you. This will be a nice little exercise. I'm going to make this an exercise. And I will, when I write up the homework, I'm going to put some training wheels on it. So, because I understand, I just wrote this formula. Do you know how to calculate this? What's this mean?
Like how to take the integral?
Yeah, how would you take that integral?
Probably I'd do it by parts.
Do it by parts. See, but integration with respect to what? What kind of integral is that?
If it's hyperbolic, would it only be not only in respect to x?
Well, that's an ordinary kind of integration that we might see in Calc 3, but maybe we wouldn't see it in Calc. So this has to be understood like parametrically. What you do is you find a parameterization of the curve in terms of time, let's say, and then this gets replaced with dx dt, this gets replaced with dy dt. There's a dt out here, and this is the parametric function for y. So it's a lot like a line integral or a arc length integral. It's that kind of integration.
Okay, so you try to do it more like calc 3.
Yeah, it's a Calc 3 calculation. Okay, so moving on here. So, okay, great. It turns out, and I'm not going to prove this, that the hyperbolic angle is actually the same as the Euclidean angle. It just happens through the way the geometry works out that the concept of angle is the same. And there's some other happy coincidences that I'll explain here in a moment. But so angle's still just the same. So that's angle. So if we talk about right angles in the hyperbolic plane, they're just the ones that are familiar to us as right angles. All right. So what's a line in the hyperbolic plane? See, so now we have to address the question: what's a line in an abstract geometry? All right. What's a line? All right. So that requires a little bit of creativity, but We take the viewpoint that a line is the path between 2 points in the space which has the shortest distance. I mean, certainly that's the case in Euclidean space, right? It's as the crow flies. Well, unless the crow could tunnel through the earth, I guess. I mean, the crow actually flies over the surface of the earth along a great circle. That brings me to yet another geometry called spherical geometry, but one thing at a time. So what's a line? It's a geodesic is what it is. What is a geodesic? This is the shortest path with respect to the distance function of the geometry. So I stated the difference function. I stated the distance function of this geometry at the start by that integral. That's the definition. And so in hyperbolic geometry, it turns out that the geodesics in the hyperbolic plane, there are two kinds of things that are geodesics. So this is a theorem. In the hyperbolic plane, the geodesics are either vertical lines. I should say vertical rays because we can't have a line. I mean, well, I don't know. When I say vertical ray, that's sort of from the Euclidean perspective, isn't it? But the vertical line, a line that just goes up and down in the y, x is fixed. Or semicircles terminating on x-axis. Well, asymptotically to the x-axis. Nothing actually gets to the x-axis because that's not part of the space. But just to, so basically these guys are geodesics, except I need to fix that, right? If this is my x-axis. And also these guys. These kinds of curves, these are the geodesics. These are the lines in this space, actually. And again, I shouldn't draw it down here. It's not down here. And really, if I was more careful, I'd always draw my x-axis dotted, since it's not part of the stupid space. But anyway. So those are your geodesics. What I'm about to tell you has really not much to do with anything else. But it's also amusing that a circle, what would a circle be in a geometry? Like, how would you define? I would define a circle to be the set of points equidistant from a central point with respect to the distance function. Now, another hilarious quirk of the hyperbolic plane is that Euclidean circles are actually still circles in the hyperbolic geometry. But here's where it gets weird. They're not a circle with respect to the same center. They're a circle with respect to a modified center. So the point set of the circle is still a circle, but it's a circle with respect to a different center. So like if this is the circle in the Euclidean sense, and I think it needs to be, it's got to be like the x-axis has got to be down here, like that. Of course, we know that that's the Euclidean center, right? Like HK. The hyperbolic center is big HK, and I don't know if it's above. It's on the same. Guys, I'm not sure. Let me think about this for a second. Equidistant. It's got to be lower. It's got to be down here somewhere. Because basically the idea of the hyperbolic plane is that the ruler gets longer and longer and longer. Like your infinitesimal measuring ruler gets longer and longer and longer as you approach the x-axis. So that means that if that point, these points from here to here, these are further apart than it looks like in the Euclidean sense. Whereas these are, this distance and that distance might actually be the same in the hyperbolic geometry, because we're dividing by y in the integration. So it counts parts of the curve which are smaller y as being longer. And so the formula for h and k, like h, I think I can fit it here. H actually is equal to square root of k squared minus r squared. And r, for what it's worth, is 1/2 the natural log of k plus r over k minus r. And this little r is the Euclidean radius of the circle. So, like, I don't know, if I was the mathematician who first understood this, I would have been like, what? I would have been expecting, like, the hyperbolic circle to be, like, part of a hyperbola or something. I don't know, just not a circle, but yeah, it's a circle. But it's a circle with a weird center.
Yeah, that's where you're losing me. Like, are you saying, like, that center is like, there's two centers and, like, they're both basically hyperbolae?
No, what I'm saying is that with respect to Euclidean geometry, the Euclidean circle is the set of all points, which is the same distance with respect to the Euclidean distance function from the center. We're used to Euclidean distance, right? It's the square root of the change in x squared plus the change in y squared, right? Just the length of the line segment, the displacement from one point to another. But the hyperbolic distance is given by that integral. So what this theorem is saying is that if you pick this point down here, this distance, the distance from this center point to all these points around, it's the same with respect to the hyperbolic distance function. And all of these points are distance big R away from the central point with respect to the hyperbolic distance function. Yep.
On the square root, is that an h or an
I think it's a k. I believe. Sorry about that. All right, so, I mean, yeah, when I read that result, I was also kind of like,
Is it saying, like, the area of these points is the same? Like, that's why it's respecting to that?
well,
So, like, if you took the integral of any part of the curve, that would be the result of that one, like, strand?
yeah, I mean, it's saying if we parameterize the line segment from this particular point to any point on the circle, and we ran that line segment, the length of that line, that if we ran that line segment's parameterization through that integral, we get the same value, and that value would be big R. It's the set of all points that have the same hyperbolic distance from the central point. And and when I say central point, that's also loaded, right? Because when we say central point, we already have a Euclidean bias, right? For us, the central point is the little hk, not the big hk. But with respect to the hyperbolic notion, the center's down there. It's dragged down. That's just weird. But anyway, hey, listen, guys, we can make a whole course just out of doing this. Like, it's enough for a whole course, really. So let's go back to Playfair's postulate for this hyperbolic plane, right? These are lines, right? These are lines. So what does Playfair's postulate say? It says, given a straight line M and a point P not on M, all right? And geodesics are straight lines, okay? Even these semicircles we consider straight lines from the abstract perspective. So if you just, here's a straight line, let's say S, here's a point P, not on that, right? And how many parallel lines are there? I mean, how many straight lines are there that go through that point P? Right? What's that? Infinitely many, right? There's the vertical one like this, right? And then you could take this one, right? You could take this one. I'm going to run out of chalkboard. You know, you could take this one. I mean, you could just, there's like, yes, there are infinitely many. So again, hyperbolic half plane satisfies postulates 1, 2, 3, 4, right? But it does not play nice with Playfair's axiom. So this example shows you concretely, right, that it was not going to be possible to prove that the fifth postulate of Euclid followed from the first four. Because logically, this hyperbolic plane has the first four, and yet it doesn't have the fifth one. Now you could say, well, there are other things to Euclidean geometry besides those four postulates, and those would forbid this happening. And you'd probably be right. But that wasn't the question. The question was, given just the first four postulates, can we prove the fifth? That's what mathematicians were trying to do. And it can't be done.
What made them think of using a hyperbolic plane instead of a normal circle?
So Carey is, their inability to prove the fifth from the first four is the one thing. But that's a good question. Like what? So that's actually very good. Who first looked at the hyperbolic plane? I don't. I know that it's often called the subtitle of this book is the Poincare half plane. So I'm sure Poincare had a lot to do with this. I don't know if he's the originator of this. There are other versions of this geometry, this hyperbolic geometry, that are not quite the same. Like there's other things that are sort of like the same almost thing as this, but they're a different point set. There's a couple different versions of this, and it's not. But you mentioned area. Area's got a different definition here too. Area, when you calculate area, you don't just integrate dx dy. You integrate dx dy divided by y squared. So like hyperbolic area is also mangled.
Okay. Is that why the trig for hyperbolic stuff is way different than the trig normal?
Yes. In fact, there's also a law of cosines for hyperbolic geometry that is different than the law of cosines. It involves cosh. There's a law of sines that involves sine and sinh. There's also a law of cosines and a law of sines for something called spherical. So I haven't talked yet about spherical geometry, but there's also a spherical geometry, right? And spherical geometry also can be shown to satisfy the first four postulates. And so the lines, spherical, in fact, I mean, an easier way to give this talk probably would have been, I think the spherical geometry is less condemning to the Euclidean geometry because of a quirk of spherical geometry. What does spherical geometry look like?
And for this, you said that the Playfair's postulate wouldn't work in a hyperbolic.
Right, because we have picked a point that was not on the straight line S, right? And we found not a unique, but infinitely many, in fact. But just two would be enough. It's an embarrassment of riches. So spherical geometry is the geometry which is natural to a sphere, right? And you can study spherical trigonometry and so forth. But in a sphere, if you're on a sphere, right, what's the shortest distance between 2 points? What line goes from here to here? That's the shortest line. Yeah, if you're not allowed to go through the sphere. He's no allowed. What's that? It'd be a curve. What kind of curve? A space curve. If I could draw it worth anything, but I can't.